Hi, my name is Romain Edelman. Jadamza, Victor Kunchak, and myself are very happy to present our paper, Zippy LL1 Parsing with Derivatives. We present a parsing algorithm for LL1 languages using derivatives and zippers. Our approach occupies a very interesting place in the design space of parsers. First, it naturally supports a parser combinators interface, which makes the approach easy to embed in functional programming languages. Next, it guarantees linear time parsing thanks to the restriction to LL1 languages. Parsers can be statically checked to ensure that they belong to this LL1 class. Thanks to our use of parsing with derivatives, the state of the parser is represented as a reified expression, which makes it easier to support features such as reassumption, prediction of next tokens, error recovery, and so on. Finally, the approach lends itself well to verification in proof assistance. Using the coq proof assistant, we have been able to formalize our approach and verify its correctness. Parsing is a process of converting token sequences into structured values. Generally, a description of the syntax is also given to the parsing algorithm. In our case, we will use a context-free expression. Context-free expressions, that we call syntaxes in our paper, are a combinator-based formalism for describing relations between token sequences and values. The set of syntaxes for any type T is built inductively. We start with a few basic syntaxes. We have the LM syntax, which associates sequences of only one token to the token itself, provided that they are of the correct kind. Token kinds represent groups of tokens. For instance, if we have the tokens foo, bars, bar, the token kind could be ident. If we add tokens 3, 42, and 17, the token kind could be number, while if we add the strings world and hello, their kind would be string. Token kinds are useful because they abstract away details that are unneeded for recognition, but are important for building up the resulting value. Next, we have the epsilon v syntax, which associates to the empty string the value v that is tagged to epsilon. Finally, we have the bottom syntax, which doesn't associate any sequence to any value. It represents the empty language. To build more interesting syntaxes, we use a set of combinators. The first one that we use is disjunction. The disjunction between S1 and S2 behaves as either S1 or S2. Next, we have sequencing. The sequence S1 followed by S2 produces the value V1 paired with V2, provided that S1 produces V1 on a prefix and S2 produces V2 on the rest of input. Then we have the map combinator, which allows for a function to be applied on the parsed values. Finally, we have recursion thanks to an environment which binds a finite set of identifiers to a unique syntax. Let's have an example. Consider that you want to associate to n a's followed by n b's the value n. To do this, we simply have the variable x syntax, where x maps to the syntax lma followed by var x followed by lmb, on which we map the function f, which simply increments by 1 the value returned by the inner var x, or we take the disjunction with epsilon 0. It is sometimes easier to visualize the syntax as a tree. Here, the var x is a single node. The syntax associated to x in the environment is also a tree, which is rooted at the disjunction. Usually, parsing algorithms will not work directly on such a syntax representation and rely on some conversion to some sort of automaton. In our approach, we avoid this conversion entirely, as our algorithm operates directly on syntaxes. To do so, we make use of the concept of derivatives introduced by Brozovsky in 1964 for regular expressions and generalized to context-free expressions in 2011 by Might, Dare, and Spivak. The derivative of syntax by a token is itself another syntax. A syntax S associates the token sequence T followed by TS with the value V, if and only if the derivative of S by T associates TS with V. To know what values V a syntax S0 associates the tokens TS with, It suffices to repeatedly apply derivation for all input tokens and then check what values are associated to the empty string by the final syntax, a much easier problem. In 2016, Adams, Hollenbeck, and Might showed that the technique has worst-case cubic time complexity. Despite its elegance, the technique shows poor performance in practice. With this work, we propose a linear time parsing algorithm based on the same principles. Of course, terms and conditions apply. Our approach is restricted to LL1 syntaxes, where all ambiguities can be resolved using a single token of lookahead. We now briefly discuss some properties of syntaxes that we will use to first statically check that the syntax is LL1, and two, guide the derivation process. The first property that we look at is productivity. A syntax is said to be productive if it associates at least one token sequence with a value. We derive productivity according to inductive rules. Nullability asks the question, what values V are associated with the empty string by the syntax S? Again, we derive nullability using inductive rules. The first set of a syntax S is a collection of all kinds which can start valid sequences, described by S. The membership of a kind in the first set of a syntax is given by those inductive rules. The next property we introduce is should not follow sets. A kind is part of the should not follow set of a syntax if it would introduce an ambiguous choice when directly followed by a syntax that starts with a given kind. Kinds are added to the should not follow set in case of disjunctions, when one side starts with a kind and the other is nullable. Should not follow sets are propagated to parent syntaxes according to those rules. We can finally introduce the notion of LL1 conflicts. Conflicts are introduced in three cases: when both sides of a disjunction are nullable, when both sides of a disjunction can start with the same first kind, and in case of sequences, when the should not follow set of the left-hand side is incompatible with the first set of the right-hand side. When a syntax has no conflict, we say it is LL1. We are now finally equipped to define derivation of LL1 syntaxes. We only define the derivative of a syntax S by a token T when the kind of T is part of the first set of S. When the kind is not part of the first set, the derivative is trivially bottom. In case of an LM syntax, the derivative is simply an epsilon syntax. For disjunction, it suffices to derive on the appropriate side according to the first set. The same applies for sequences. Derivation continues on the right when the left is nullable and the kind of T is part of the first set of the right side. Otherwise, derivation continues to the left. Here, the function nullable is used to get the unique value associated with the empty string by the LL1 syntax S1, if any. Cases for map and variables are equally simple. Let's go back to our example syntax and observe a few derivations. Let's start with our initial syntax var x. When we derive it by a, we get the following tree. When that tree is later derived by a, we obtain that larger tree. If we were to derive it by a again, we would obtain that last tree. If we were to do a careful analysis of the algorithm, we would see that it has worst-case quadratic complexity. The problem is that every time we derive, we start from the top of the tree, while the immediately interesting part is located deep down the tree. In this work, we solve this issue by using a zipper, that is, by having a focus on one node of the tree from which all pointers flow. This focus will let us start right where the last derivation ended. We call the syntax in focus the focal point, and all nodes from that point to the root of the tree layers. A focus syntax is a pair of a syntax S and a context C, that is a stack of layers. There are three types of layers: follow by layers, which indicate what syntax follows, prepend layers, which hold the previously produced value, and apply layers, which indicate that a function must be applied on produced values. Using the unfocus function, we can move back the focus up to the root of a syntax and completely eliminate the context. The function is not used by the parsing algorithm, but is useful to reason about focused syntaxes. The function clearly shows that apply layers correspond to map combinators, prepend layers to sequence with an epsilon v to the left, and follow by layers to sequences with a specified syntax on the right. When a focus syntax is focused on an LMK node of the correct kind k, derivation by a token of that kind is trivial. It suffices to replace that LMK in focus by an epsilon t. Therefore, to derive, it suffices to move the focus to the unique LMK node. To do so, we have first to go up the layers to find a suitable syntax, and then go down that syntax towards the LM node. The plug function is used to move the focus to the next following syntax when the focal point reduces down to a value. The locate function is used to move the focus to the next syntax in context, which starts with a given kind, skipping nullary prefixes as needed. To do so, it uses the plug function that we've just defined. Finally, pierce is used to move the focus down a syntax towards the unique LMK node. The function uses first set to decide on which side to recurse. Note that its structure is similar to the one of the simple LL1 derivation procedure. Derivation is then trivial. We first query the kind k of t, and then we locate that kind within the focus syntax sc. If the location is successful, we pierce that new focus syntax and replace the LMK node by an epsilon t node. Parse is equally simple. In case the input token sequence is empty, we call the result function to get the value associated with the empty string by the focus syntax. Otherwise, we take the first token and we derive the focus syntax by this. If successful, we get a new focus syntax S prime C prime, which we recursively parse with. Let's have an example. Let's consider the usual var x for the language AN and BN. If we derive by A, first we have to locate the node which starts with a token of kind A, which is simply var x, and then we use pierce to go down to the LMA node and replace it by an epsilon A. Note that the epsilon A is now the focal point. We then derive by A again. We first locate, which moves the focus down to the var x node. And then we pierce that var x again, and we obtain this tree. The focus is now on the new epsilon A at the bottom. If we were to derive by B now, we would locate, which would move the focus to the LMB node, and then we would pierce, simply replacing it by an epsilon B. If we were to derive it by B again, we would have first to locate the B, which would move the focus up the tree to the LMB node, which we would then pierce. And then finally, we would call this result function to get the result, which is sum 2. The runtime complexity of the algorithm is O of n, which is an improvement over top-down parsing with derivative algorithms. The algorithm has been implemented as part of Scallion, a scalar parser combinator library available on GitHub. Here we see the syntax of the library to define syntaxes for array values, bindings, and object values for a JSON parser. Notice that we can use higher level combinators such as repetition with separations, and so on. We have compared the performance of our approach on JSON parsing. The column for simple represents the original LL1 parsing with derivatives without the zipper. The Zippy version is with the introduction of the zipper. The SPC column indicates the result for the scalar parsing combinator library, a parsing combinator library that uses recursive descent. We see that our approach had similar performance to the standard parsing combinators library. In addition, we compared it with Antler. Even though we don't rely on any form of code generation, our approach is only 3 times slower than an Antler-generated parser. Among the features of Scallion, we have the possibility to statically check that a parser is LL1, and in case it is not, to get the list of conflicts. We can also predict the next token, for instance, using first. We could also enumerate the token kinds that form valid JSON values. Scallion also has support for residual parsers. If we were to feed a Scallion parser incomplete input, for instance here, we would get that the end is unexpected, and we would get no value. But every result contains a description of the syntax either at the point of error or at the end of parsing. We can use this syntax to continue parsing or to query it. For instance, here we can query what is expected next. If we were to give it more tokens, we would get a successive pass, and we would get directly the array value that corresponds to 1, 2, 3. We have proven the approach correct in Coq, and the proofs are available online on GitHub. The formalization is about 9,000 lines of code, and at the very end, the parse algorithm is correct. For future work, we would like to extend this approach to arbitrary context-free expressions and not only LL1 expressions. And we have already an implementation of this on GitHub. We would also like to enrich the set of combinators that is available. In particular, we would like to support the monadic bind combinator. We're looking forward to your questions. Thank you very much.